Okay. To talk about the difficulties or challenges in that, there are three hazards. One is structural hazard. Okay. So in the structural hazard, we call this structural hazards. This is happens because at a given time, if multiple instructions trying to access the same resource, that is structural hazard. Second one is the data hazards. When there is a instructional dependencies, okay, so the second instruction depends upon the result of first instruction, then it has to wait until the first instruction completes its execution. So that we call data hazards. It happens when both the instructions are having dependencies. The third one is the control hazards. The branch target will be computed at the end of in the execution stage, and the result will come at the end of execution stage. So up to the from instruction fetching stage, instruction decode stage, and instruction execution stage, whether that branch instruction will be taken or not taken in the future is unknown. So if any instructions following that branch, it has to wait until the previous instruction in the pipe is executed. So these are three main hazards. So let's first look at this structural hazard first. So if you recall our previous slide, assume that there is a program. That program is having the four instructions, sequence of instructions, and assume that these instructions will be allowed inside the pipe, okay, inside this pipe sequentially, or we can say that linearly. Okay. So now you tell me instruction 1 enters into the pipe, correct? In the second cycle, instruction 1 enters into the instruction decode stage of pipe. So instruction fetching stage become free. So instruction 2 enters into the pipe. So there are two instructions in the pipe. One is the instruction fetching stage, which is utilizing instruction memory, and the first instruction is utilizing the hardware component, that is register file. So at the third cycle, as usual, the instruction 1 enters into execution stage, instruction 2 enters into the next level stage, instruction decode, instruction 3 enters into the entry level of the pipe. Then at the fourth cycle, instruction 1 moves to the next instruction, that is memory access stage in the pipe, and instruction 2 moves from instruction decode to execution stage, and instruction 3 enters into instruction decode stage, instruction 4 enters into instruction fetching stage. So now, as per structural hazard, do you find is there any problem at the fourth cycle? That's correct. Instruction 1 is also accessing the memory, and instruction 4 also accessing the memory, because in the instruction fetching stage, same functional unit will be used. So at this stage, at the fourth cycle, two different instructions trying to access the same memory unit, that is memory. So then there will be a deadlock. Okay, does that make sense? That's the reason I ask you to remember which components are using in different stages. Is that make sense now? let's continue. In the fifth cycle, the instruction 1 moves into write back stage. In the second instruction moves into memory access stage, and third instruction moves into execution stage. Fourth instruction moves into the instruction decode stage. So at this stage, is there any structural problems? The hardware problems are there. That means you can see instruction 1 is using for writing the data into register file, and instruction 4 is trying to read the data into register file. Correct? Register file. Here the data is reading. Here the data is writing into the register file. So same hardware component is accessed by instruction 1 and instruction 4 at the fourth cycle. So here, if there is no, so this problem we call the register file read-write structural hazard. And here is the memory access read-write structural hazard. If this problem is not there, then these 4 instructions, they complete their execution with this pipeline in 8 cycles. If these problems are not there, then the execution smoothly take place. So they complete in 8 cycles. But if the problem is there, then what is the solution? Isn't it? So just recall here, the solution is separating this memory unit, which is accessing, okay, the memory unit here and here. Just separate this memory unit as instructional memory in the instruction fetching stage and data memory in the memory access stage. So that's why, if you recall the Harvard architecture, in Harvard architecture, if you recall the diagram ALU, okay, just let me use this space. The ALU, and one side the component instructional memory, second side the memory access, means data memory, and other functional units. Is that make sense now? The first solution is separating the memory is one solution. If you have, based on Moore's law, if you have more functional unit, I mean, you have more transistors, you can build more functional units, and separating one is memory unit, another one is instruction memory unit, another one is data unit. So this is one of the solution. And second solution, as Kasmi mentioned in the chat box, yes, the next instruction has to wait. That we call stall the pipeline. So the solution is just look at find the solution for here, dividing the memory. This is the data memory. So the data, instruction 1 is writing data into data memory, whereas the instruction 4 is fetching from the instruction memory. Yeah. So in this, if you look at here, if the signal is 1, this is high, right? This data path. And if it is 0, this data path is low. Okay, this data path. That means when the single cycle is divided into the single cycle is divided into, suppose, 2 parts. One is the single cycle divided into 2 parts. One is the high signal, second one is the low signal. So in the high signal, in total cycle, this is as one cycle clock signal. So here the data will be right. and here the data will be read. The second means this one is 0, this one is 1 in representation. So this total is known as one cycle. So in this stage, if it is divided into first half is used for writing and second half used for reading. So from this entire signal at the stage 5, okay, from that port, if the first half used for the write, second half used for the read, so the first instruction writes the result into write back, and in the second half, instruction 4 read the data from the register file. So this is the second solution by utilizing the clock cycle. Okay. So that is the memory stage only access read or write data. So the next solution is the second one as we just discussed. Does that make sense now? Okay. So the second solution is, if you observe here, the single cycle is divided into two parts, first half for writing and second half for reading. So that way, if you think about that, the fifth stage of executing these instructions, okay, look at the first half instruction will write into the register file, and the fourth instruction in the second half cycle reads from the register file. So by adding, the clock technology. Okay. So with this, by adding the extra hardware, that is data memory and instruction memory, and utilizing the clock technology, first half for write and second half for read, these four instructions will smoothly executed by, okay, these four instructions smoothly executed by the pipeline processor in how many cycles total means they executes in 8 cycles only. They executes in 8 cycles. If not, they must stall the. These are two solutions, but the common solution is, if not, as Cosme mentioned, the fourth instruction must wait until the first instruction write in the fifth cycle. That means it is not allowed inside the pipe. Okay, so at this stage it will not decode. It will allow the pipeline, but it's not decoding because register file is busy, so it stalls its execution. It stalls its execution here. So that we call fill with the bubble in this pipe. So then at the sixth cycle, it enters into the fourth instruction, enters into instruction decode stage, then it go on execution stage. So the number of cycles will increase up to 9. The execution completes in 9th cycle. The execution completes in 9th cycle. So this is the structural hazard and their solutions.